Okay, it is a great pleasure to be here at this event and tell you about a different perspective of how we view quantum technologies through the lens of translational applications. My name is Stefan. I work at Sandbox CQ. I founded a quantum sensing team at this company. Just very briefly about Sandbox, we are working on intersection of AI and quantum. Without hype language, what this means in more practical terms, we're working on simulations for drug discovery. We're working on post-quantum cryptography and security. But today I want to talk to you about our work in sensing. We're using magnetometers to navigate the planet using crustal field of the Earth without GPS. But what's more relevant for us today is discussing the medical imaging hardware that we have been developing. We have started our work in 2017, 2018 as part of the Alphabet family. In the meantime, we fundraised, we spun out. Starting 2022, we have been an independent startup focusing on these three pillar technologies. Okay. Translational applications of quantum sensors is an interesting topic and something I never really thought about how to concretize until I was invited for this workshop. And the reason why I think it's interesting is that even for the last 2 days, hearing the speakers, I would bet that everyone in this room has thought about translation in one way or another. And because of this, I don't think there's one way to present this. It's a very personal thing. It's a very contextual thing about the technology, the application, the market, and everything that goes with it. Just let's take a couple of examples. So we heard yesterday about, let's say you want to do a population screening for COVID-19 using your breathalyzer. You have to think about translation, moving it from the bench. We heard 2 applications of microplastic detection as well. Well, if you want to do it at scale, you need to think about translations. Maybe you don't care about this at all. Maybe your grant funding agency requires you to put a paragraph or 2. Well, you will have to think about translation. And today I heard a wonderful startup idea about improving optical transparency of koalas to build your own remote controlled army, which is, I have questions, but if you want to do that, you will have to think about translation at scale. So it's a complex topic. There's no one way to do it. There's no rating authority on translation. Today you have me, so you will hear kind of my perspective on how we do this at Sandbox. Translation is also an interesting term because it also talks about different languages. You want to translate from one language to another. And here I want to call out some terms in 2 distinct camps and how we can kind of use the polarity between them or investigate polarity between them. In one term, we are driven by discovery. We conduct research. We ask, is it possible? Our audience that we have to persuade is mostly a reviewer. They care, is it novel? They care, do we understand it well? And what is the perfection? Or did we understand it to the full perfection? In the other camp, things are quite different. We care about applications. We develop products. We almost always want to start knowing that it's possible. So now we have to think about, is it practical? Is it scalable? In the medical device space in particular, our audience is a regulator. And let's say for FDA, the 2 questions that FDA cares about is what is the safety and efficacy? And this is kind of formal FDA requirement. Perfection is often frowned upon because it takes time to develop it. But if you specifically have VCs breathing down your neck, speed is of premium. These are more than just syntax divisions. Infamously or famously, a director of Google X, Astro Teller, banned the word research from slides. He thought that it indicates unbounded, infinite problems that will never converge. And the whole premise of Google X is trying to fail fast. Figure out if it's not going to work so that you can move on to the next problem. More recently, in one of the more unhinged posts by Elon Musk, he talks about banning the word scientist from his companies, talking about how there may be second-tier engineers or so. So these are very polarizing topics, depending on which camp you're sitting in. If you want to do translation, if you want to learn languages, I'm going to use my little helper here, which is the Duolingo bird. And I will use him to put in the following slides wherever I think there is interesting concepts that are related to translation. So whenever you see this guy, that's where I think there's something that is connected to translation or learning how to transform between one to another language. As I said, it's a very personal topic, depending on which field you work on. I come from the Diamond Quantum Networks community, actually, but in Sandbox, I started developing quantum sensors using NV, quantum magnetometers in particular. So today I want to tell you about the state of magnetometry and how concepts of translation apply to the various magnetometers. Again, this topic is much more comprehensive than this, but I think magnetometers really showcase in a great way the whole complexity of the topic. In this fantastic paper of 2020, Professor Mitchell and Professor Alvarez talked about the known landscape of magnetometers to date. And as you can see, there is a zoo of technologies that they classify on two axes. One can be understood as sensitivity, and another can be understood as spatial resolution. And starting from here, first you see that it's a very busy plot with a lot of different tools that can do your magnetometry job. But if you're thinking about research, if you're sitting in camp number one, you would think about pushing the boundaries of the unknown. So you would push either this plot to the left, trying to detect smaller and smaller features, or you would try to push this part down, trying to detect more and more sensitive magnetic fields. Let's dive into these two extremes, because if you think about what is the advantage of quantum, you either want to go small or you want to get super sensitive. So let's dive into these two extremes and think about maybe showcase that how translation manifests in these two fields. So on one side, if you care about extreme spatial resolution, this is the part where NV reigns supreme mostly. We already heard a couple of talks on this, so I won't spend a lot of time. I just want to call out three really nice applications that are conducive to discussing translation. In one of them, the functional nanodiamonds are connected to a certain drug. They are then forced to attack either a bacteria or a cancer cell. And then as the free radicals are emitted during the cell death of let's say, of bacteria, you use T1 relaxometry and measure the efficacy of how drug at the spot where it reacts. So it's a fantastic work. Couple of groups do this. This is work from Schierhagel lab in Groningen. And there is a little company called QT-Sense that they just spun out maybe 2 years ago that is trying to commercialize this technology. Below, taking a little bit of a different angle, you're looking at living objects and trying to optically image magnetic particles within them. This is the magnetotactic bacteria. And inside of them, you can see that this is some of the work from Professor Walsworth, where they try to use quantum diamond microscopes, so bulk diamonds, but in wide field imaging to try to detect at a very high spatial resolution magnetic particles inside that can organize along the axis of this bacteria. Again, there is a company called QCAT, Quantum Catalyzer, that's spinning out different companies actually from Walsworth Lab, and this is one of the fields of their focus. And then finally, maybe the most well-known, one of the pioneers of diamond quantum technology, even regardless of sensing, is QDTI, that uses shallow NV centers to detect in an ultra-sensitive way proteins, nucleic acids, and cells. And all three of these companies, what they have in common, apart from the philosophy of graphics design for the logos, they are also really focusing on translating work that has been developed from academic labs that they come from into the companies and trying to develop products out of them. Again, there's been a lot of conversation about this, some presentation on this topic. I won't spend a lot of time on this part to say that this is one area of translation or work. If we look at the bottom right part, we can forego spatial resolution, but really try to build the most sensitive magnetometer that we can. And if you think about what is the killer app, what are the greatest uses of very sensitive quantum magnetometers, this is detecting biomagnetism that's produced by human organs. In this fantastic plot, they plot magnetic field strength that a certain organ wiring of a certain organ produces, placed on the x-axis, which is the frequency bandwidth. So you can see that as you go from the bigger muscle to bigger muscle like a heart to a smaller object, you can see that you traverse heart, muscle, brain, nerve. I think I've seen a paper working on magnetoretinography recently or so. So this is to say that if it has wiring, if it has nerves, you can try to pick it out and turn it into a diagnostic tool. Our little Duolingo bird says there's already a couple of companies working on MEG, the first three, field line, circumagnetic, and mag for health. And also in the MCG work, which I'll talk to you a little bit more about later, there is also a couple of companies focused on this. Now, if you're only focused, if you're sitting in the camp number one, you would try to build better and better sensor to push this sensitivity lower so you can access these type of more and more applications. But what the language of application tells us that these two axes is almost table stakes when you want to commercialize. Yes, you need to have a sensor that has exactly the sensitivity you need and the spatial resolution if you care about this. there's a whole array of dimensions that you have to think about when you want to move from writing scientific papers to pushing products out. Some of them, I try to rank them by my priority for applications that I'll tell you about: size, weight, power, and cost, of course, cryogenic applications, ease of use, robustness, scalability, dynamic range, you name it. Depending on the application, you will use one or another. This is to say that just looking at 2 parameters is not enough. You need to use many. And I will tell you, spend the remaining of my talk talking about a very specific application and some of the cautionary tales and approaches how to really incorporate this whole complexity of different parameters into your choice of technology. With this, I want to dive even deeper. So we went from sensors to magnetometers. Now we're going to go from magnetometers into a topic that, in my mind, displays the translational applications in their full power. So I want to tell you the history of and the state of the art of magnetocardiography, MCG. Usually I would tell this story from the perspective of quantum, especially if you want to talk to investors or doctors. They're wooed by the stories that won't work in this crowd. So I'll tell you more about cardiology. And so after this talk, I want to share with you how heart works, what are some of the biggest problems, and then how you want to tackle them. All right. So Hollywood might make you believe that heart attacks are these huge dramatic events. You go into the hospital with a chest pain, you're immediately put on a crash cart, you roll through the emergency room, go to surgery, or so there's electrodes, there's all sorts of wiring. That's not really, that's how it works. Yes, in some cases, if your heart damage is quite high, meaning that you have arteries blocked, there is a limited blood supply to your heart, this causes your cardiac cells to die. If the problem is incredibly large, if a large chunk of your heart cells have died, you will, in this electrocardiogram feature, see an abnormality. Each of these 3 peaks, P, QRS, and S, and T wave, are certain wirings of your heart firing, and this is what electrocardiograms pick up. These are these electrodes, and this is mostly when you look at Hollywood movies. This is what these like beeps are presented in the shot. So by law, if you are admitted with chest pain to the hospital, within the first 10 minutes, they have to apply electrodes on you and measure this ECG. And if the doctors see that this ST signal, which is actually just a little bump, if they see that it's elevated, that is an indication of the large amount of heart death, and you're rushed immediately for surgery. It's a very clear case. This represents less than 1/3 of all heart attacks. And not to say that a lot of patients that have surgery are actually healthy. And this indicates that we have really large gaps in diagnosing heart attacks. That's why this problem is #1 cause of death globally. What is more common, that you are admitted with chest pain, you're either healthy, but we don't know that yet, or there is a very insidious amount of damage that's either deeper inside your heart muscle or small. Your heart cells are dying, but not at the rate and at the level where EKG can pick it up. And this is called non-ST elevated myocardial infarction. But doctors don't know this yet because they put electrodes on you, everything looks normal. So what do? They keep you for observation. They draw your blood, that takes a couple of hours. They measure this enzyme that's released when your heart cells die, but it takes a long time and it has a large amount of false positives. So it really triggers in cases where it also shouldn't. So oftentimes this is not really a useful tool. So then you're either kept for observation, you're put on a treadmill to increase the blood demand to exacerbate the problem, or you're sent to MRIs, to surgery, to radioactive screening. These are all more complex, expensive, and invasive tools. If we look at the very intuitive model of the wiring of the heart is a weird pump. So it has a different muscle that squeeze at different times. And the electricity that causes this squeezing can be approximated through current flow, right, through the wiring. So a healthy heart, let's say, has a very uniform conductivity. And I think this is the extent of physics, the right-hand rule that I'll tell you today, which is that as the heart, healthy fibers conduct electricity, they will create magnetic fields in and out of the screen. So if you're able to build a magnetic field camera and snapshot this magnetic field, you will see this very orderly 2-pole fingerprint that will tell you something about that actually your fibers are healthy. However, let's say you have a heart attack, there's a cardiac damage, let's say in this place here, well, the current is then diverted. So diverted current creates a more complex patterns in these weird psychedelic blobs. So if you had a 2D imager of magnetic fields, you would be able to take these screenshots and then classify them to say, is there a heart disease or not? And this is what magnetocardiography is. So it has been shown in the last decades to be able to correctly classify this insidious and extremely prevalent type of heart attacks, where they measure time and time again between healthy volunteers that have this stable pattern and patients with end-stage heart attacks that have this all over the place, this magnetic field fingerprint. This technology is older than MRIs, right? This is 69. Professor Cohen at MIT was sitting in this lunar module of a shielded room to measure using superconducting detectors magnetic fields of the heart. And since then, there's been a lot of research in this area. So if this is so great, why don't we have this in every hospital? I've never heard about MCG before joining Sandbox, and we started thinking what we should be doing. Based on a very scientific Twitter poll for cardiologists, 90% of them have also never heard of MCG. So what's the catch? And the catch is that magnetic fields are really, really difficult to measure. There have been companies, a handful of them in the US, Germany, Korea, and Japan, that have been pushing these MCG devices that you can actually buy on the market that produce these amazingly accurate images and already showed clinical power of this technology. Some of them, called geneticists, use spin exchange relaxation-free OPMs that require magnetic shielding. Some of them required cryogenic cooling. But if you think about going back to the plot that I showed, yes, they match well when it comes to sensitivity and other parameters, but there is a huge gap between what clinicians need in the emergency room and what this technology requires. There's no available rooms in the ER where this can be done. Cryogenic is expensive, and you need to screen patients very quickly because every minute counts when you're having suspected of heart attacks. In this great review paper, one of the grandfathers of the field, Riccardo Fenici, with his son Peter, talked about this gap and how we need reliable, user-friendly, unshielded devices. And this is where I want to kind of call out the gaps in translation. Even though this is technology that's 50 plus years old, the translation means you have to deal with other parameters and other parts of your multi-dimensional axis, not only the performance itself, which is table stakes. Okay, so you need to choose the right tool for the job. And as you can see, like MCG is what around the picotesla level sensors or below. And it's a busy space with a lot of magnetic sensors that can access this regime. So we need to understand the applications and choose the right one, which is exactly what I didn't do when I joined Sandbox. As I mentioned, I come from the Diamond Quantum Networks, and I joined with a mission to build the best NV magnetometer for MCG. So I had this sensor-focused approach. I was sitting squarely in the first camp, really starting with the technology itself. We spent 2 years to make a little compact module that we can then use and test. And to my knowledge, in 2021, we've measured the first MCG, human MCG in our lab, making it ready for the hospital. We wanted to ship it as quickly as possible. We wanted to test it in the field. So we actually packed this up into this large box. And your sensor is right here, close to your chest. And we wanted to start a clinical study at UCSF, which we did in 2021. And we absolutely failed in this study. I'm not trying to write a paper here, so failures are celebrated. Failures are also give you great stories if you manage to overcome them. The study at UCSF that failed, and you can see here, this is the readout of one of the sensors. I was telling you, you need 10 picotesla or so. This is 10,000 picotesla of noise. So what this tells us is we are dealing with building great sensors is blessing and a curse. They will pick up all sorts of things you don't want to pick up. So you're really looking at a needle in a haystack, this small amplitude of heart magnetic field in a huge environment of the hospitals. The reason why it failed, so look, if this was an academic talk, I would probably make the full 30 minutes about how we did this and the whole details of this sensor and how we measured this. Now it's just a footnote to tell you, and I can go on record to say that at the state of the technology NV sensors are at right now, they will not be able to commercialize for MCG, and I can go on record to say this. There are many reasons for this. One of the main reasons is that in order to deal with this large amount of noise suppression that you need to achieve, what helps is the plurality of sensors. You need a lot of sensors, 50 or 100 or even more than that. And NVs are just not at the level where you can create that many of them, string them in a system, and then not use the 10 kilowatt laser that the previous speaker talked about, because NVs are also power hungry if you want to squeeze out the last pieces of sensitivity. So we had to go back to the drawing board and think about revisit both our technology choices, but also our identity, because we decided we cannot be sensor focused anymore. We have to be application specific and choose the right tool for the job, which meant scraping envy. And I can tell you more about it, why we did it. But it also came as a surprise to me because I joined wanting to make this technology work, and we just had to abandon it. So we started exploring what other sensors are out there that we can use. And we found an unlikely candidate in geo-exploration. The total field OPMs have sensitivity needed to access the MCG. We found a company called Geometrics that could sell a couple of them to us, and we started testing them in the lab. They are room temperature. They have a correct swap. The cost is a bit too high, but their robustness and their system integration is excellent. So we could just purchase a lot of them, string them into the system, and start testing how will it perform once we deploy it in a hospital. So we started building it in our lab. This is our lab in downtown Palo Alto. You can go and visit. And we started to simulate and inject hospital level noise that we already knew how it looks like from our deployment, and see if this will be resilient enough to be able to pick out these hard features. So this is how it puts together. This is actually real data from the hospital, from actually our next clinical study that came after UCSF, that we started with, again, a string of sensors that are overwhelmed by noise, and then we use the system architecture and AI to denoise the signal. AI is great at two things. One thing that I'll tell you about right now is that it's great at pattern recognition. All hearts are kind of the same. They all have similar features. And once we deploy our system to the hospital, we usually measure for 24, 48 hours without any patient to learn what type of noise is present in a hospital. Our first UCSF study was killed by elevators and mostly, and other kind of hospital workflow magnetic interference. And that's what AI is really good at, learning what type of noise comes from where and in what type of day. So once you do your system architecture, all sorts of radiometry, PCAs, ICAs, you name it, there's a lot of them. AI as well helps. And then you're able to clean out this signal, and then basically each place where you park your magnetic sensor, you will be able to get the readout from that location in order to reconstruct the map. So in a dynamic way, you can take millisecond by millisecond of this slice and reconstruct this 4x4 grid to see the evolving magnetic field as your heart operates. And then we, again, take these snapshots to create these funky blobs that tell us, is there a heart attack? Now, these blobs are not meant to be read by a human. AI is also great at the second thing, which is classification. Is it a cat? Is it a dog? Is it a healthy or an unhealthy patient? There is a wealth of biomarkers sitting in these blobs that AI can pull out, and that's something that actually we spend most of our work, engineering work these days, trying to pull out relevant biomarker features from these two. What I didn't mention, and I just want to go back, I didn't pitch you MCG well enough, because the reason why it works is because magnetic fields propagate through human body in a transparent way. So the panels that we create, and you can see one of them here, actually work without contact. So there is a little air gap between these two, and this is critical for many applications. There's absolutely no contraindication because the patient they almost do an airport scan where they take all of their metal parts and then they hop on this chair, and in 5 minutes they can get a scan using the magnetic field sensors without any contact. So we just get them as close as we can to boost the signal, but that's pretty much it. MCG is, because of this reason, is used for fetal arrhythmias. There's not a lot of ways you can measure fetal function of fetal heartbeats. You can do ultrasound, but that's a mechanical. But using MCG, you can really measure directly image fetal function using this type of technology. All right. So we wrapped it up in a lab. This is our system. It's called the Cardi AQ. It's on a little bed, unshielded. And once through all of the kitchen sink of tools we can apply, we saw that we have some amazing state-of-the-art magnetic field maps in our lab. This is also reproduced in a hospital. There's a couple of papers we already published in American Heart Association, TCT, and we're from the clinical studies that I'll tell you in the next slide. Now, you chose the best sensor for the job, and then you build a system that can make the most out of it. Is your job done? Well, I think you will all agree that quantum physicists should not be touching patients with heart attacks, which creates a problem. And the problem is the systems we are building will not be used by physicists. They will be used by our wonderful study coordinator, Sajini. This device right now is in Mount Sinai West emergency room, scanning patients coming from the street with suspected of heart attack. And Sajini is our wonderful coordinator, does not care, surprisingly, if it's quantum. She could not care less. She doesn't even care if it works. The only thing two things she cares about: one, how quickly can she get the patient out of this, unhook the patient from our system if the patient starts getting a heart attack while doing the scan, and two, how easy it is to move this hoof and move the bed around. And this is kind of lesson 3 of translation that we learned, is that we need to pick out the feedback of end users as early as possible, because they will find edge cases, problems, and intended use much better than physicists in the lab can. You can spend months or years optimizing for parameters that no one cares about, or you can really send it or enroll people to come to your lab, do functional testing, and tell you really how it should be done. Right now, our system can be trained, coordinator can be trained in 1 hour. This is now sitting both in Mount Sinai. We already finished one study, 2023. We started a new one, and in Mayo Clinic as well. In Mount Sinai is enrolling people coming from the street with chest pain. At Mayo Clinic, it's actually sitting at surgery, scanning patients before and after surgery in order to see the magnetic field fingerprints when they have stenosis and afterwards, after the occlusion has been removed. So is this the end of the story of translation? You chose the right sensor. You build a system that can make the most out of it in the field. You build it with the feedback of someone that's actually going to use it. Well, not really. And my kind of personal, things I spend the most time on these days is on this very complicated plot, which is to say that even if you build the right thing with the right feedback, that doesn't mean anyone's going to use it or anyone's going to buy it. US healthcare system is a complicated topic that I cannot go into today. It's enough to say that on average, there's been a recent study that says that 6 years after getting the FDA approval is an average time of getting coverage for medical technologies these days in the US. And this is to say that you need to not only look at engineers, patients, and doctors. There is a very complex field of stakeholders that will decide if your product will live or die. And that's maybe the final boss of translation is getting specifically in the medical device field, is getting through the hump of this incredibly complex space, and something we spend most of our time on these days. All right. So with these 4 key messages of translation, starting from application focused and sensor agnostic all the way down to many stakeholders, I want to wrap up this part. I'm very excited to hear how different experts in the field approach the topic of translation. Rebecca Frank-Hayward, there's already a huge popular demand from the previous session to hear how she has been applying her work at the company. And John will tell us more about the work done from Walsworth Lab that I touched on previously. So with this, I can thank you and take a couple of questions as Rebecca sets up.
You said you were going to pick the best sensor, and so the total field OPM is the best sensor.
It's not.
Wait a minute. What is an OPM? You didn't tell us that.
The optically field magnetometer, optically pumped magnetometer, atomic vapor cell that has been shown to have incredible high sensitivity in different regimes. The one we have chosen operates without shielding. It's in a total field regime. So right now, it's the sensor that gives us data, but it's by no means the perfect sensor. One reason is it's $10,000 per channel, and we need 50 channels to do a proper noise subtraction. If you go to an emergency room and try to pitch them a $500,000 system, they're not going to buy it. So we are still on the lookout for different sensor technologies. Once you're sensor agnostic, that means you can try, test, and work with different technologies as well.